Um, so, so the outline of what we're going to talk about, we're going to start with some introduction, some background material. We're going to be focusing, the main object are going to be Calderón-Zygmund singular integral operators. That's what we're going to focus on today. And a particular inequality that is sort of crucial to the theory of Calderón-Zygmund operators. We're going to talk about a few different proofs for how this can be proved. And then we're going to generalize and study these techniques and these ideas in some different settings. So in the linear setting, in a multi-linear setting with some different smoothness assumptions, and in tracking down some dimensional dependence in specific situations. So let me first define the objects that we're going to be studying. So we're going to be talking about Calderón-Zygmund operators. These are singular integral operators. So they're going to be defined by integration against some kernel, and the kernel is going to have a singularity. So the kernel we're denoting by K is going to be a function that takes in two variables. It's not going to be defined on the diagonal. So when the two inputs are the same, it's just not going to be defined. That's why this is kind of coined singular integral kernel. But we need to impose some conditions so that the theory actually will flow. So we have these size and smoothness conditions. The first condition is that the kernel is going to decay at worst like 1 over the difference of its inputs to the dimension power. So it's not going to really be integrable. This is sort of the borderline case with this exponent where it's not going to be integrable at the origin or at infinity. It's singular, but we also impose this other condition where we can control the size of the difference of the kernel with different inputs here. So the gain here is that we have some positive delta. And now instead of just having an n in the denominator, we have an n plus delta, which gives you a little bit of a gain. You have some higher integrability. And this is really just, this is a smoothness condition because if we divide, say, the x minus x prime to the delta over, that looks like a difference quotient on the left-hand side, and you're saying that the derivative is controlled. So given one of these functions, you can define a Calderón-Zygmund operator. So the Calderón-Zygmund operator is going to, in an appropriate sense, be defined by integration. Take your input function, multiply it by your kernel, and you integrate that with respect to y. So the y dependence is gone, and now this is a function of x. So this is how the operator is going to be defined. You assume a priori that the operator is going to be bounded on L2, and this is an appropriate representation of our operator. Okay. So these are important for many reasons, many reasons. A big theory that's been studied systematically since the 1950s, and I guess even before in certain cases. And some prototypical examples include the Hilbert transform. So the Hilbert transform, denoted by H, is given by this formula. So in this case, the kernel is 1 divided by x minus y, I guess with this normalization constant 1 over pi. This is something that you may have seen, for example, in Fourier series, the convergence. So we want to understand how Fourier series converge back to an original function. And the pointwise convergence isn't really the right way to interpret this. So you can interpret the convergence in LP. The LP convergence of Fourier series is in some appropriate sense equivalent to the LP boundedness of this operator, the Hilbert transform, or really its cousin operator, the conjugate operator, but same sort of thing. And in higher dimensions, the role of the Hilbert transform is played by the Riesz transforms. So this looks a little complicated, but here the kernel is this factor, this constant times the jth component of x minus y divided by the modulus of x minus y to the n plus 1 power. So if you take n equals to 1, this formula just collapses and gives you the Hilbert transform. These are the higher dimensional analogs that you may have seen. Okay, so these are both examples of Calderón-Zygmund operators, and we want to study the broader range of Calderón-Zygmund operators more systematically. So what types of properties do they have? Which ones are important? And so for example, any Calderón-Zygmund operator, we assume a priori that it's going to be bounded on L2, but actually with the assumptions that will extend, and any Calderón-Zygmund operator will be bounded on LP for any p that's bigger than 1. Okay, and just as a reminder, if we're not working with LP spaces so much, the LP space is a set of functions where this P norm is finite. So you take your function, you raise it to the P power, integrate it, and then take it to the 1 over P. So this is an important property of Calderón-Zygmund operators. And what I was thinking about and working on is thinking about what happens in the case when P is equal to 1. We have a parentheses here, so the P equals 1 case is not included with this inequality. So we want to think about what actually happens when P equals 1. Could we turn this parentheses into a bracket and actually include it? Turns out we can't. So the inequality fails in general when P equals 1. And you can see that by considering the Hilbert transform. If you compute the Hilbert transform of just a characteristic function of an interval, you can actually directly compute that and you get this logarithmic expression. And that function is not even in L1. So there's no way that the Hilbert transform could be bounded on L1. If you have an L1 function, this easy characteristic function, the image under the Hilbert transform is not even an L1 function. But we don't give up there. If it doesn't satisfy the L1 inequality, then let's look for a replacement. So the replacement is, well, it's not strong type 1, it's not bounded from L1 to L1, but it is bounded from L1 into a slightly larger space, this weak L1 space. So the quantity, instead of having an integral, we look at these level sets, and we say that this is uniformly controlled lambda times the level set where TF is bigger than lambda. We look at the measure of that, and you take the supremum over positive parameters lambda. This is what defines our weak L1 space. So you can see that L1 is contained in weak L1. It's a bigger space. That's a simple consequence of Chebyshev's inequality. And it's actually going to be a strict inclusion. You can look at like 1 over X, for example, in 1 dimension, which would not be in L1, but it would be in weak L1. So any Calderón-Zygmund operator, although it's not bounded on L1, it does have this weak type 1 property, which is actually, this is sort of the crucial component for proving the LP bounds on the previous slide. You, together with the a priori assumption of the operator being bounded on L2, once you prove this weak 1 property, you then use an interpolation argument to deduce the LP bounds for the P's bigger than 1. So this is really where the difficulty is. So let's talk about how this is proved. Classically, it's proved using a method called the Calderón-Zygmund decomposition, which that decomposition relies crucially on the doubling condition of Lebesgue measure. So what does that mean? In general, if you have a metric measure space X with a Borel measure mu on it, we say that's doubling if the measure of an inflated ball, say twice the radius, is comparable to the measure of the original ball. So clearly, this inequality going the opposite direction is always true because of just set containments. But we're insisting for the doubling property that we're actually going to have those two measures will be comparable to each other. So we have to assume that the measure of the bigger ball is controlled above by maybe some constant times the smaller ball. So that's something that we exploit in a lot of settings. And that's exploited in proving the Calderón-Zygmund decomposition, which allows us to prove our weak 1 inequality. So that's how it's classically done since the 50s. In the 90s, Nazarov, Trail, and Volberg asked a question about what happens. Can we develop a systematic theory for Calderón-Zygmund operators in a setting where we don't have the doubling property anymore? So if we get rid of that, maybe replace it with a different condition, can we still get a nice theory of singular integral operators? So the condition that they imposed, so they forgot about the doubling condition, but instead considered a polynomial growth condition. And these abstract spaces are typically referred to as non-homogeneous spaces. So a non-homogeneous space is a metric space with a Borel measure such that the measure of balls grows no worse than some polynomial in the radius. Okay. So this is a different condition from the doubling condition. We're not saying that, but still is related to the size of the measure of a ball. So in their IMRN paper, Nazarov, Chill, and Volberg in '98 proved a lot of things about Calderón-Zygmund operators in non-homogeneous settings. But one and the important thing for our talk is that they prove that the weak L1 inequality holds. So the same thing is that this is an abstract space. We're looking at the mu measure of it rather than the Lebesgue measure. But they got the same inequality in this setting by avoiding the double win property. So they must have developed a new technique, right? Because the Calderón-Zygmund decomposition crucially relies on the doubling property, as with some other parts of the proof of the classical proof. So to achieve this goal, they had to come up with a different proof. And what I did for my PhD thesis was basically looking at their proof, looking at the classical proofs and trying to play around and see how they can work in different settings. Okay, so I want to describe these two proofs that I mentioned first, and then we'll talk about some applications and some results. So the first observation is, since the Lebesgue measure on Rn, just the classical setting, the volume, the Lebesgue measure of balls, it's just comparable to the radius to the dimension. In particular, Lebesgue measure satisfies both the doubling property and the polynomial growth condition. So both of these methods make sense in the classical setting of Lebesgue measure on Rn. So I want to describe first the classical Calderón-Zygmund decomposition proof in the context of Lebesgue measure on Euclidean space, and I'll also want to describe the Nazarov trail and Volberg proof in that setting as well.
Cody, may I ask a question here, please?
Yep.
Yeah, so in classical case, they use this decoupling, and for this Nazarov trail Volberg technique, they use this with RM, right?
I'm sorry, what was the last thing you said?
For this NTV method, they use this definition in this page, right?
Mm-hmm. Yes.
So what's the difference that they have this, instead of the decoupling, they have this one?
Yes. Yep.
Okay. Thank you.
Right. Yep. That's the difference. Yeah, in the classical setting, oops, I want to go up. In the classical setting, I know I stated this just for Rn, but you can define Calderón-Zygmund operators in a more abstract setting where you impose this condition on the measure, and then the same proof essentially works in that setting. So if you're in an abstract setting where you have this doubling condition, then this proof will just essentially work. And they considered an abstract setting where instead of the doubling condition, you have this condition instead, and they developed a different proof to obtain the analogous inequality. Okay, so let me describe these two proofs, but just in the easier, the more classical setting of Euclidean space with Lebesgue measure. Okay, so let's talk about the Calderón-Zygmund decomposition method first. So what do we want to do? We're going to be fixing a L1 function f and a positive parameter lambda. It's going to be like our cutoff for this level set. And we want to prove this inequality, where maybe there's some implicit constant, but that constant does not depend on lambda and it does not depend on f. So what we do is we apply this Calderón-Zygmund decomposition, and what that lets us do is split up our L1 function into two functions, G and B. G stands for good and B stands for bad. And then the bad function can be further split into countably many pieces, Bj, where they satisfy some properties. So the good function, we call that a good function because it's bounded. It's going to be controlled in L infinity by the parameter lambda, by this cutoff of the level set, and it's going to be controlled in L1 by f. The bad function is potentially unbounded, but it's going to have some properties which save us. So each of these pieces that comprise the bad function b, they're going to be supported on pairwise disjoint cubes, Qj. So they're supported on cubes, and the size of their support in total is not going to be too large. It's going to be controlled above by exactly the expression we want to bound everything by. Okay, so the size, although the bad function is bad, it's going to be supported on a set that has good measure. It's not going to be supported on a really large set. Each of the BJs are constructed so that they have cancellation. So they have mean zero. They all integrate to zero. And each of the BJs are going to be controlled in L1 by this quantity lambda times the measure of its support, which will allow you to prove that B in L1 is also controlled above by F in L1. Okay, so there's, I mean, I'm just stating this as a theorem. This is what the decomposition lets you do. We can split up into the G and the B, and these functions have specific properties that allow you to do different techniques and prove our inequality. There's actually some work behind this that I'm not saying. It involves studying averages of your function f and splitting based on, typically write this as a stopping time argument based on the size of different averages. But one thing I do want to mention is that the doubling property is used in this decomposition. So to get these conditions that I've highlighted in red, that crucially uses the doubling property. Okay, so when we're going to talk about in a couple slides this Nasaroff-Chill-Fulberg technique, they need to do something different to still get these types of structure, but without using the doubling property. Okay, but once you have this decomposition, what you do, again, we want to prove this inequality right here. So what we're going to do is take the left-hand side of that expression, write f as a good function plus the bad function, use linearity of our operator t, and then this is really just a set inclusion. You can split it up. If tf is bigger than lambda, then tg must be bigger than lambda over 2, or tb has to be bigger than lambda over 2. So you can split it up in studying t applied to the good function and the bad function separately. Then what we do is we consider the support of our bad function b. Remember, each of the bj's that sum together to give you the function b, each of them are supported on a cube, which we denoted by qj. So what we're going to do is consider that cube and enlarge it by an appropriate dimensional constant, and then piece all those together. We're going to call that exceptional set omega star, but it's essentially just an enlarged version of the support of b. That's going to give you some space that will allow you to invoke some properties of the Calderón-Zygmund kernel and perform the estimate. So then what we're doing, this first piece is the same as this first piece, but what we're going to do is take this set here involving b and intersect it with our enlarged support of b and its complement. So we're intersecting with omega star and omega star complement. So we have 3 terms that we'd like to estimate, which you can estimate each of those 3. I'm just going to kind of say out loud the idea. So with the good function, this takes just a few lines of work. What you do is you do Chebyshev's inequality with a power equal to 2. Then we're going to use the a priori assumption that t is a L2 bounded operator to get rid of the t in that side of that expression. Then you use the fact that the good function g is bounded in L infinity by lambda. So that will get you from a power of 2 to a power of 1 on the exponent of g, and it will give you a power of lambda to the first power in the denominator here. And then use the fact that g is bounded above in L1 by f in L1. So just a few lines of work. Chebyshev's inequality, the a priori boundedness, and the conditions on g allow you to get this inequality, which is good. That's exactly what we want to bound it by. The measure of this set omega star, that comes from the fact that by the doubling property, the measure of each of these qj's, qj star is going to be comparable to the measure of qj by the doubling property, and then the sum of the measure of the qj's by the property in the Calderón-Zygmund decomposition is less than or equal to 1 over lambda times the L1 norm of f. So this is going to involve the doubling property and then the property from the Calderón-Zygmund decomposition about the size of the qj's. We can also bound that above by the quantity we would like, then we're just left with this term, which you can also get that inequality. That involves a Chebyshev's inequality with a power equal to 1. So you're doing an L1 estimate, and you can look at the integral of t applied to b, split it up into each of the bj's. Each of the bj's integrate to 0. They have this cancellation. So that allows you to introduce a term where you can subtract off a term with the kernel evaluated at the center of the set qj. And then since we have this difference of the kernel of x comma y minus the kernel evaluated at some point that's somehow close by, and since we have the separation that we've guaranteed by enlarging these sets qj to qj star, that allows us to use the smoothness estimate of the kernel to get some sort of integrable expression that allows us to eventually control everything by the L1 norm of b which is then controlled above by the L1 norm of F. So this one uses the L2 boundedness and the properties of G. This one uses the doubling property and the fact that the size of the support of B is not too large. This one uses the smoothness estimate of the kernel and the mean zero of each of those bad functions Bj. That's the crucial idea. And I just want to emphasize again that this uses the doubling property. So you can't just enlarge in the same way here if we don't have a doubling property. And I guess implicitly, these other conditions, properties of the Calderón-Zygmund decomposition, also rely on the doubling property. But that's how this inequality is classically proved. Now I want to talk about this other proof that was given by Nazarov, Trail, and Volberg, where they avoid the doubling property. So there's some clear places where they need to make changes in the original proof. The idea is roughly the same, like the philosophy of the proof by splitting up into a good piece and a bad piece is that's still the general philosophy of what we're trying to do here, but you have to do it in a different way. So instead of doing a Calderón-Zygmund decomposition where you have to carefully study averages and do a stopping time argument, instead, we're just going to set omega, our exceptional set, to just be where F is larger than lambda itself. So there's no maximal function involved, there's no averages. You're just looking at where F is larger than lambda. Then you can apply a Whitney decomposition, which is basically breaking up as long as F is lower semi-continuous, which by density you can assume this set here is going to be an open set. So you can apply a Whitney decomposition, which is basically breaking up your set omega into a bunch of dyadic cubes, such that the size of the dyadic cube is comparable to the distance to the boundary. So if you have like a circle, you're gonna break this up into a bunch of cubes. The larger cubes are going to be more towards the core, towards the inside, and you're going to have smaller cubes closer and closer to the boundary. But then you'd break up your entire set into a bunch of these cubes. Then what you do is just look at G. G is going to be defined to F restricted to the complement. So clearly G is going to be a bounded function because on the complement of omega, this inequality goes the other direction. And your function F is going to be less than or equal to lambda on that set. So it's still we're using G for a good function as well because it's going to be bounded. B is just going to be F where it's larger than lambda. And we're going to split that up into a bunch of BJs where we restrict F to these Whitney cubes that decompose omega. So with this decomposition, you can still split up F into G plus B. G is still going to be bounded in L infinity by lambda and controlled in L1 by F just because it's a restriction. The BJs are still going to be supported on pairwise disjoint cubes such that the total measure is less than or equal to 1 over lambda times the L1 norm of F, because we can apply Chebyshev's inequality to the measure of this set up here. That's exactly what we would get. And the B is controlled in L1 by the L1 norm of F. Now there's some properties that we don't have. We don't have really any L1 control on BJ itself. We have L1 control on B, but on each of the BJs, we don't have L1 control. We also crucially don't have the cancellation. We don't have the fact that the integral of BJ equals 0. That's not something that we have in this case right now. Okay, so here it's a little bit of a simpler decomposition, but we don't have as many properties. But we also did not use the doubling property. So with this decomposition, we still attack the proof in roughly the same way. We split up F into its good piece and its bad piece. You estimate these level sets with F replaced with G and F replaced with B. And we're going to intersect the term involving B with the support of B and its complement. Notice here that I didn't change this to an omega star. I didn't inflate anything because we don't have the doubling property. This is actually just the support of B itself. So this first piece we can handle in exactly the same way as in the classical proof of Calderón-Zygmund decomposition. So that one's going to be okay. This term here, we have the measure of omega. That's also less than or equal to what we want to bound everything by, 1 over lambda times the L1 norm of F, just by Chebyshev's inequality. That was on our previous slide. But we need to work harder to understand how to control this last piece involving T applied to B. So in particular, we don't have the cancellation of our BJs here. So we can't do the same trick as in the previous situation where you subtract off the kernel evaluated at a point and then use the smoothness estimate. We can't subtract it off because the BJs don't integrate to 0. So what we do is we force cancellation to appear. So that's why I'm defining this stuff up top. So let's just fix, let's say xj is a point inside of qj. Maybe it's the center, doesn't really matter, but let's just say that we have a point inside of qj. I define this number aj to be the integral of bj, which is not necessarily 0 in this case. And then I'm going to define this linear combination of Dirac masses. So this is a measure, a sum of point masses, where the location is going to be, say, the center of the QJs, and the coefficient, the weighting of each of these point masses is going to be given by the integral of bj. So what we're going to do is add and subtract and apply essentially triangle inequality to look at b minus nu, and then study t applied to this linear combination of Dirac masses separately. Now this term here, we forced cancellation because we're taking b and we're subtracting off measures that are weighted by the integral of bj. So now if we split it up into the bj minus these terms, aj, delta, xj, each of those terms will now have cancellation, which will then allow us to subtract off a term with the kernel evaluated at a point, and then invoke the smoothness estimate of the kernel and do essentially what we did in the previous proof with the Calderón-Zygmund decomposition. You can use an L1 estimate with Chebyshev's inequality, subtract off the kernel evaluated at a point using the cancellation that we forced, and then use the smoothness estimate of the kernel, which will allow you to get some integrable quantity that we can then control above by the L1 norm of f. So the crux of the Nasaroff-Chell-Volberg argument, by doing a simpler decomposition, they reduce matters to proving the estimate on a linear combination of Dirac masses. That's really the idea, the main idea that they have. You reduce the weak L1 to studying the weak L1 on a linear combination of point masses, which is a common theme in harmonic analysis. Typically, I've heard it referred to as a pointillist principle, where you reduce matters to studying these like singular measures, these Dirac masses. So we claim that this is true, that you can actually bound this above by 1 over lambda times the total variation of nu, which by construction is going to be less than or equal to 1 over lambda times the L1 norm of f, which would allow us to complete the proof. Now, I wrote this as a claim. This is actually where the hard work in their proof is. This will take a few pages to prove. So let me just make some comments. So it is involved. It involves approximating each of these point masses by pairwise disjoint Borel sets that have an appropriate measure. Then we can use the size condition of the kernel, the polynomial growth condition of the measure, which we haven't really used at any point yet, and then a duality trick that involves the adjoint to control some maximal truncation operator, and then that would and the control of the maximal truncated operator to get this inequality. So there's some work that's involved, but I'm just there's not enough time to go through everything, so I'm going to hide that. But the point is we have two proofs that work in the Euclidean setting, for example. One is more adapted for homogeneous spaces where you have a doubling property. The other one is adapted for non-homogeneous spaces where you might not have a doubling property, but you do have a polynomial growth condition. So just like the way that I wrote it, both of these work in this classical easy setting. So just restating the theorem from earlier that motivated this whole discussion. So with respect to Lebesgue measure on Rn, we know that this is true. So the first idea is, well, the Nasaroff-Chell-Volberg proof definitely works here, but what if we allow the doubling property again? Can I study that same proof, but also use the doubling property, and maybe things can be a little bit easier still? So that's the first result, is a new proof of this classical theorem, where you follow the general Nasaroff-Chell-Volberg scheme. You do the same decomposition where you just look at the set where f is larger than lambda. So you don't have to do this Calderón-Zygmund decomposition. You don't have to study the averages in the way of decomposing into the good function and the bad function. But also, we avoid this claim that involves the point masses. So the difficulty in the Nazarov-Trail-Volberg argument is also avoided. So therefore, we don't need to use the size condition of the kernel. You don't need to use the polynomial growth condition or duality or the maximal truncated operator. Instead of approximating by point masses to get your cancellation that allow your L1 estimate and the smoothness estimate of your kernel, instead you directly approximate each of these BJs, which did not have mean zero at the time, directly approximate them by the pairwise disjoint Borel sets of appropriate measure. And then we add in these Borel sets or slightly enlarged versions of these Borel sets into our exceptional set, which due to the doubling property will also have good measure. So the first result is a proof that's inspired by Nazarov and Trail and Volberg's argument, but it avoids the difficulty of both the Calderón-Zygmund decomposition and the difficulty of the point mass estimate. Okay, so now we have a handful of proofs of some inequality, and we would like to apply these proof techniques and see what we can obtain. So one setting that we can also discuss are weighted settings, which is a big area on its own. So I'm just going to talk about one inequality just for the sake of time. But what a weight is, basically the idea is, can we change the underlying measure? Instead of having Lebesgue measure and get these LP inequalities and these weak L1 inequalities, the idea is for which absolutely continuous measures will the LP bounds for the Calderón-Zygmund operator still hold? Or for which measures absolutely continuous with respect to Lebesgue does the weak L1 inequality still hold? Turns out that the correct assumption for such measures is this AP condition. So we say a weight is a function that's positive almost everywhere, and it's locally integrable. So it makes sense to describe the measure of compact sets, for example, or cubes. And we say that it's an AP weight if this condition holds, that these averages of the weight and the weight to the 1 minus, this is the Holder conjugate exponent, p prime, so 1 over p plus 1 over p prime equals 1. If the product of these averages is uniformly bounded over all cubes q in Rn. So that's the AP condition. It turns out that this is the correct assumption to put on weights for the LP theory to hold. And there's an appropriate definition of this when p equals 1 as well. But there's this theorem that says that if you have a weighted setting, you have a weight that's an AP, then you can get a weighted weak L1 inequality, and it can be quantitative in this way, where you have the weight on the inside of the operator and you counter with a reciprocal of the weight on the outside of the operator. And then you're measuring the weak L1 with respect to that measure W. You have this on the other side too, L1 of W. You still get the weak L1 inequality in this weighted setting with this quantitative dependence of a linear and the AP characteristic times this logarithm. Now, if you take the weight just to be the constant function 1, this completely reproduces the classical weak 1-1 inequality. So this is a weighted generalization. They call this a Sawyer type mixed weighted weak type inequality. The first proof was given by Ambrosi, Perez, and Recchi in 2016. Their proof is a variant of the classical Calderón-Zygmund decomposition, and in the same paper from the result that I had in the previous slide. You can use that same proof technique where you sort of simplify the Nazarov-Trail-Volberg inspired proof, and you can obtain this weighted inequality as well with the same quantitative dependence. Okay, one other setting that people study that's been more popular in the last 10 to 20 years or so is the multilinear setting. So now we're going to consider multilinear versions of these singular integral operators. So we're still going to have, so what we're going to do is we're going to take in a tuple of functions. So we're taking in m functions, and it's going to return just one function instead of taking in one function and returning one function. And we need to impose, the operator is going to still be defined by integration against a kernel. Now our kernel is going to have more variables, but it still needs to have a size condition, and it still needs to have a smoothness condition for the theory to flow. When you take m equals to 1, then these are the same exact conditions that I had on the first slide, but this is a multilinear setup. And then the multilinear operator is going to be defined similarly again when m is equal to 1. And this is the same definition as what we had on the first slide, but this is the multilinear version. So you're going to assume that the multilinear Calderón-Zygmund operator is bounded a priori on a product of some spaces into another Lebesgue space. This is like the analog of the a priori assumed L2 boundedness of your operator, and it's going to be given by integration. So in I think it was 2002 or the early 2000s, Grafakos and Torres sort of systematically made the theory of Calderón-Zygmund, of multilinear Calderón-Zygmund operators for this setting. And in that paper, among many other things, they proved an endpoint weak type estimate. So if you take a product, a tuple of functions that are all in L1, so your Fi are in L1, then your multilinear Calderón-Zygmund operator will send that tuple boundedly into a weak type space, where it's a weak type L1 over M space. So if M is equal to 1, again, this will give us our classical weak type 1-1 inequality, but this is our multilinear version of this. So the first proof was given by Grafakos and Torres in 2002. It uses the Calderón-Zygmund decomposition. There are a few other subsequent proofs. One I found of Maldonado and Naibo in 2009. They're really studying some things with pseudo-differential operators, but their proof again uses the Calderón-Zygmund decomposition. And then Perez and Torres, they considered a slightly different smoothness assumption on the kernel. They proved it using the Calderón-Zygmund decomposition. And then we have another proof that uses this Nazarov-Chill-Volberg method, a multilinear version of that with myself and Brett Wick from 2019. Okay, so we talked about two different applications that generalize the classical inequality. One was to weighted settings, another one was to multilinear settings. So I think a natural question to ask is, can you get a multilinear and weighted inequality at the same time? And that's the next result that I want to talk about. So there is a theory of multilinear weighted inequalities in harmonic analysis. And it turns out that the natural assumption to put on weights is this expression here, which admittedly this is a lot for one slide, but the idea is we still want to have a different measure on each of the input Lebesgue spaces and on the output space where we study our multilinear operators. And it turns out that the correct assumption to put on your weights is using with this multilinear AP condition. So this W with a vector, that's a tuple of weights, all positive almost everywhere locally integrable functions. This VW is a product of the weights to a certain power. And we assume that the product of these averages is uniformly controlled over all cubes Q and Rn. Again, if M is equal to 1, this reduces to the standard AP condition from a few slides ago. It turns out that this multilinear class can be related to the linear AP classes. So a vector of weights W is in the multilinear AP class if and only if this product weight to the certain powers is in the linear A M times P class. And each of these components of the vector of weights to the 1 minus Pi prime power is in a linear class A M times Pi prime. And if you track down their proof, you can get some quantitative dependence that involves this way. Again, a lot to see, but the point is that there's a relationship between the multilinear classes and the linear AP classes, and you can make it quantitative. Using this, we can prove a multilinear weighted version. So if you take a tuple of functions that are in L1 with respect to different weights Wi, then your multilinear Calderón-Zygmund operator will send the product of F1 times these weights, and then you have to counter, just like with the linear weighted inequality, you have to counter with the reciprocal. It'll send that boundedly into the weighted weak L1 over M space, and you can get a quantitative dependence as well. So if you take all of the weights just equal to 1, this reduces to the multilinear weak 1 into 1 over M space inequality. And if you take M equals to 1, this reduces to the mixed weighted weak type inequality. So it generalizes both of the previous results in certain senses. So in this paper, I gave two proofs. One uses the Calderón-Zygmund decomposition, and it's based off of the proof of Perez and Torres from 2014. The other one uses the Nazaroff-Chell-Volberg method, which generalizes the result that I previously had with Wick and actually simplifies it as well. We kind of avoid the point mass technique in this paper. Two other applications that I want to talk about briefly in the last, I guess, 5 or 10 minutes or so. One relates to the smoothness of the kernel K. So like I said earlier, when we were describing the Calderón-Zygmund decomposition proofs and the Nazaroff-Chell-Volberg proofs, in estimating the term that involves a bad function, it's crucial that we have some cancellation, which will allow us to subtract off the term with the kernel and then use the smoothness assumption on the kernel to estimate that term. So that's crucial. We need to have some smoothness on the kernel in order to obtain the weak L1 estimate. So the question is, how much smoothness do we need on the kernel? So typically a strong version, and we're just going to be talking about the convolution case just so the formulas will look a little bit nicer. A strong version of the smoothness is that you can actually control, maybe your function K is differentiable. You can actually take the gradient, and the gradient would be less than or equal to 1 over x to the, say, n plus 1. So some increase, some number bigger than n. So that's a stronger version. That would imply this version here, where we take a difference of kernels and we get this type of control, which this is similar to what I had in the first slide. This is typically called a Lipschitz condition. And actually, this would imply this integral smoothness condition, which was introduced by Hormander, this one's actually what you would need to naturally complete the proofs that we were discussing earlier. So this is typically the hypothesis that I would work with in this setting. But the question is, can we weaken this? Can we weaken this any further? So in a paper that from 2019, I believe, we introduced a different version where, if we notice on this previous slide, this is really, since we're taking the supremum over y's of this function here, which is really a function that depends on y, this is sort of an L infinity condition, because I'm saying that this function that I have in these parentheses is controlled in L infinity. You're taking a supremum over y's, and then it's going to be bounded. So we can actually give a different version that's going to, instead of having an L infinity norm of this function here, which depends on y, we're going to consider averages in an LR norm. So we're going to look at the average, integrate y in a ball, and then divide by the measure of the ball. So this is an average over this ball of radius r. And then we're going to average the LR norms of this quantity. This coincides with the Hormander condition when r is equal to infinity. And for other r's, we have this natural nesting of these spaces. So if we call H infinity the set of kernels that satisfy the Hormander condition, and HR the set of kernels that satisfy this version, by Holder's inequality, you can see easily that this conclusion actually holds. And I need to mention something here, because there were some follow-up works which actually prove that these are equality, which is not at all obvious. Only this inclusion here is pretty obvious from the definition, but these actually are equal. So I don't want to dwell too much on this result anymore, because from subsequent works, we found out that these conditions are equal, although some subsequent works introduced a new condition, which is even weaker, which actually is strictly weaker, and it would be a proper inclusion. So you can actually make this will be less than properly some Hormander condition where you have some sort of BMO assumption. So I just don't want to dwell on this too much, but although this, I had to mention what I know to actually be true following our work. But there is a weaker condition where you do get a fruitful theory that is strictly weaker. But what we were able to prove is that under this assumption, if you have one of these weaker conditions where the kernel is in some HQ prime, then you would get a weak type QQ estimate. So it's going to take functions that are in LQ, where Q is going to be some number potentially bigger than 1, and it would take that into the weak LQ space. And what we get by interpolation, just as the weak L1 inequality by interpolation gives you the strong type PP inequalities for P bigger than 1, or for P bigger than 1 between 1 and infinity, what we would get from this result is a strong type theorem for P's that are in this interval here. And under certain situations, this interval is going to be a strictly smaller interval than the entire interval from 1 to infinity. So we call this a limited range theorem because we got LP bounds for P's in a limited range of exponents. So we weakened the smoothest condition and got a weaker conclusion as well. Now there's a paper that came in 2021 of Suzuki, where actually in the worst case scenario, so the biggest class of those kernels, H1, he was able to prove the weak 1-1 inequality. So even in the worst case, you could get the weak 1-1 inequality, which is an improvement of what we had. So I want to mention that. And I know a few people that are in the audience here also studied some versions of this where they consider this in the oscillating case. So there are some stronger theorems that you can have in this direction. So really, according to Suzuki's thing, you can get the weak 1-1 inequality, and even in the worst case scenario, you can get a full range theorem. So you can get the LP bounds for every P between 1 and infinity. But the philosophy of weakening the smoothness conditions and seeing how far it can go, how far it can be weakened and still get a fruitful theory, there's still plenty of directions to be investigated there. Then the one last line of results that I want to mention deals with the Riesz transforms. So from, I think, the second slide, we discussed our 2 motivating operators that are within the class of Calderón-Zygmund operators. One was the Hilbert transform, and the higher dimensional analogs were the Riesz transforms. So all of the stuff that we talked about here applies to the Riesz transforms, right? That's an example of a Calderón-Zygmund operator. Everything I talked about applies in the case of the Riesz transforms. So in particular, it satisfies the weak 1-1 inequality. And what we're going to be interested in is this constant Cn. So it satisfies this inequality. There's some constant here for which it holds true. Usually I was just absorbing that into a squiggle notation, but there's some constant here for which this holds true. And the question is, what is this constant? It could only possibly depend on the dimension n. That's the only sort of free thing because this is a concrete operator. So we're going to denote the smallest possible Cn with this quantity, this like weak 1-1, I quote unquote use the word norm, although it's not a norm. But the smallest constant is denoted by this, and our question is, what is that constant? And in particular, how does it depend on the dimension n? This is something that's still unknown. Nobody knows what the correct constant is here, but I'll tell you what we do know. All the proofs that we discussed so far show that this constant is going to depend at most exponentially. So we'll get something like the square root of n to the n power. So that's really bad dependence, right? It's going to kind of grow really large in n. That can be improved. In 2004, John Ackerman proved that exponential dependence can be reduced, and you can actually put just a logarithm here. So they've used a version of the Calderón-Zygmund decomposition, where instead of looking, there's 2 main differences in its proof versus the classical one. The one main difference is instead of looking at cubes when defining your Calderón-Zygmund decomposition, you look at semi-cubes. So instead of like splitting, going from here and then going to children by simultaneously like splitting in all directions and looking at these 2 to the n different children, that gives you what 2 to the n as your dependence. Instead of doing that, you're going to go from like one big square, and then when you split in all directions at once. What they do it differently is when they go from one big square and in the stopping time argument, they just split in one dimension first. Now there's only 2 children every step along the way, and then they split that one, running out of space, but then they split into all children just one dimension at a time. So that eliminates an exponential dependence in the Calderón-Zygmund decomposition. Instead of having 2 to the n children when you do your splitting, you just have 2 children every single step along the way. And another thing which I thought was interesting was instead of when they defined the QJs stars, typically we had that was 2 times the square root of n times the length of QJ. In this proof, they define it as QJ star is equal to 1 plus 1 divided by n times QJ. Because when you raise this quantity here to the nth power, you get 1 plus 1 over n to the n, which is controlled above by the constant e, right? So that's when you do the doubling, you don't get exponential dependence, you'll actually get constant dependence. They pick up the log n in the smoothness condition in a computation that involves estimating the Hormander smoothness condition that picks up a log n. So the question is, can this be improved? Well, if you think about this Nazarov-Shale-Volberg inspired proof, what Daniel Spector and I were able to do is run that proof. Well, it's not the same proof. There's many situations where we have to do some variants, kind of similar to what John Ackerman did and otherwise. But what we can do is we can give a dimensionless reduction of the problem to studying the Riesz transform applied to Dirac masses. So here there's an absolute constant that does not depend on the dimension, such that for every f and L1, you can control these level sets above by an absolute constant times the quantity you actually want to control by, 1 over lambda times L1 norm of f, plus the level sets of the Riesz transform applied to a linear combination of Dirac masses. So if you can solve the question for Dirac masses, then that solves the question for the general weak L1. And then following that, we can prove an inequality with the Dirac masses, but we also get a log n. So the question is, can you remove the log n here? That would be really nice. But using these 2 results, we recover John Ackerman's dimensional dependence. So the open question is, does this hold? Can you actually get a dimensionless quantity? Or is the log n somehow sharper? Can you get something smaller than a log n? So this maybe has some hope for doing something, because here we can actually get an explicit formula for what the Riesz transform applied to this linear combination of Dirac masses actually is. And we really just want to work with an expression that looks like this. So there's maybe some evidence that this might work. So in 1946, Loomis considered exactly this question, but in the case of the Hilbert transform. So in this case, the dimension is equal to 1, but the number of Dirac masses in your linear combination is arbitrary. And he proved that the size of the level set is actually just equal to. So it's not even controlled. This is a little equality, it's an identity. And the constant here is 2 divided by pi. So in 1 dimension, we can get this inequality, and it doesn't depend on the number of Dirac masses. We can get an actual explicit formula. It relies on the fact that this is all in 1 dimension, and this set is going to be a collection of intervals. But that's what we get when 1 dimension and n arbitrary. On the other hand, if we look at just 1 Dirac mass and the dimension is arbitrary, then you just have your linear combination is just a single weighted Dirac mass, and you can explicitly compute what the Riesz transform applied to that is. The formula is just this quantity. Doing some algebra, you can see that this is actually just going to be, the set on the inside is actually just going to be a ball of radius, absolute value of a divided by lambda times this constant involving the gamma function, all raised to the 1 over n power. And this is a Lebesgue measure. So the size of that ball is going to be exactly this quantity. And then you can look at what the measure of a ball is asymptotically. We get this quantity. And then using Stirling's formula, we can get the asymptotics of this, which is actually going to be 1 over the square root of n. So in the case of 1 Dirac mass, the Riesz transformed constant is actually going to decay to 0, which is of course much better than the log n. It actually decays to 0, which is sort of strange. So the question is, can we do this, but replace this instead of having n equal 1? Can we do this with n equals 2, or maybe even general n? And that might get us closer to our what we wanted to prove. Okay, so I'll end here. Here are some references, and thank you all for your attention.
Okay, thank you very much, Cody, for this inspiring talk. So we are open for questions.
Maybe just one random question. Have you considered this problem in the complex settings of several complex variables?
I've done some things in that setting, so I guess you'd want to consider which operator you would want to consider, right? So I've done this a complex analytic setting that is similar to Calderón-Zygmund theory that I'm familiar with is the study of the Bergman projection, Bergman spaces.
Exactly, Bergman projection, Bergman space.
Yeah, so there people do study these same things, and it has, depending on what the underlying domain is. I mean, the theory depends crucially on the geometry of the underlying domain for the LP bounds of the Bergman projection. Let's just say that the domain is the unit ball in CN. Then the Bergman projection does have LP bounds for P strictly bigger than 1. It does satisfy a weak L1 inequality. And it even has an appropriate theory of these AP weights. They call them BP weights in this setting, defined by Becquelet and Bonamy. So I have a couple papers on these things. One, I do study the weak L1 inequality, where the underlying domain is strongly pseudo-convex with reduced smoothness assumptions. I believe we assume some C4 smoothness. And there you can still get the weak L1 inequality, and even with the weights. So that's a paper from, it should be appearing soon with Nathan Wagner.
Do you have in archive that paper?
What's that?
Do you have this paper in archive? This one?
It's on, yes, it's on archive. Yeah, it should be appearing in the Indiana University Math Journal soon as well, but it's on the archive. Yep. Now the proof of that, since we're in these complex variables in our setting, we had reduced smoothness assumptions. We have to do some more operator theory tricks to reduce to studying some auxiliary operator, which sort of mimics the Bergman projection. And to prove the inequalities there, we actually had to use a Calderón-Zygmund decomposition method. We actually had to study averages in order to get our inequality. I tried thinking about using this Nassarov-Trail-Volberg idea there. I apologize, but I can't remember exactly what the obstruction was, but there was a problem with trying to use the NTV method. But we were able to do some variant of the Calderón-Zygmund decomposition to handle this auxiliary operator, which therefore by some operator theory tricks gave us the weak L1 inequality for the Bergman projection in that setting. That's basically the limit of what I know in that direction.
I see, because there are two parts in the Bergman projection, like is good one, and the other one like close to 1
Yeah.
to the boundary, like it will be very complicated to estimate. I think like I will
right. In that setting, you don't have explicit estimates on the kernel, so you have to work with a different operator where you do have explicit estimates on the kernel.
Exactly.
Yep.
Yeah, I will check. Thank you very much. Yeah, very good.
Okay, thank you, Joel, for your question. Any other question?
Yes, I have a question. Thank you for interesting talk. First, so there are only two methods to get this estimates, right? Calderón-Zygmund method and by Nazarov and other team, right?
These are the main methods that I'm familiar with that have this. I mean, there's other ways you can do it. Even in the non-homogeneous case where you have the polynomial growth rather than the doubling, there are other methods you might want to look at. There's a paper by Xavier Tulsa where he introduces a Calderón-Zygmund type decomposition in that setting. And the other one that comes to my mind involves sparse domination. So you can dominate your Calderón-Zygmund operator by some sparse operator and then prove the weak L1 inequality for the sparse operator. So the weak L1 inequality for the sparse operator is a different proof. It does not necessarily involve the Calderón-Zygmund decomposition. Sorry, but
yeah, my question is that is possible to do in non-commutative setting on Heisenberg group, this kind of, or?
So what I'm familiar with in that setting, yes, you can do these things. I haven't worked on that personally yet, so I am not necessarily the expert on that topic, but there are papers by Jose Conde Alonso. And I think he does this with Parset. Maybe some other authors I'm not familiar with. I haven't read their papers in detail, but they have a collection of papers that study Calderón-Zygmund theory in the non-commutative setting. So I think that's probably where you'd want to look.
Okay, thank you.
Yeah, you're welcome. they do have a Calderón-Zygmund decomposition for non-commutative settings. I don't remember exactly what that looks like, but there is a version of that. There, I'm not sure if this NTV argument can be interpreted in non-commutative settings, but at least there is a theory of weak L1 inequality and LP bounds and these types of things in non-commutative settings. They prove a Calderón-Zygmund decomposition to get some results in that direction.
Thank you.
So more questions for Cody?
Yeah, one. So in this Nazarov-Treib-Wahlberg method, so how important it is that this m of r to the power m is the same for all radiuses? Because, there are places where this growth changes depending on r, or even cases where for big R you have exponential behavior poles.
So I don't think it's going, as long as you have some m everywhere, the m could change. And I don't think that's an obstruction anywhere. You would just, in certain cases, take the largest or take the smallest. If you have exponential, then things will break down. If you have exponential growth of the balls, that's a very hard question. But if you have some sort of other structure where they grow like one power of r here and a different power of r here, and maybe it's different for large or small, as long as there's only a finite number of m's, then you'll be okay. But if you're saying that it grows like a polynomial on this section and it grows exponentially on this section, then things will definitely break down. That's something I thought about, and it's for probably too much time, but that's a hard question. That's because the growth of the kernel needs to somehow match and kill off the growth of the measure. So if your measure is going to grow something like mu of the ball, if that's going to grow something like e to the r or something, then you would need to have your kernel to sort of counter that and be no worse than like 1 over something like exponential, like e to the x minus y. So you'd have to have a stronger decay on the kernel, and these things need to sort of match up. That's why in the Lebesgue measure, the measure of balls are like r to the n, and at the same time the growth of the kernel is like 1 over x minus y to the n. So these sort of match up. The r to the n is going to be canceled out with the fact that you have this n in the denominator. So if you have something where you have this condition where the kernel only decays like 1 over x minus y to the n, but the growth of the balls is exponential, that doesn't match up, and you're going to have way too much in the numerator to get your estimate.
Thank you. Any other question? Hao Sang, maybe you can.
Yes.
Okay.
Okay. So the risk transform is bounded over LP with dimension independent constant, where you can use a proof using some transference identity, for example, by Bezier. So have you tried this approach to study the weak 1-1 constant?
Yeah. So the proof that I'm familiar with the dimensionless constants for the LP bounds uses this method of rotations where it reduces matters to studying the directional Hilbert transforms. And yeah, that's the natural thing that you would like to do in the weak L1 case, and I have tried to do that. The issue was, oh my gosh, this has been like 2 years at this point, so it's hard for me to remember some of these things. So how does the proof work in the LP case? There's this Minkowski integral inequality. I think the issue was there wasn't an appropriate Minkowski integral inequality, which would allow you to switch the order of integration. I believe that might have been some part of the issue. I apologize. Maybe I can't answer your question fully off the top of my head, but if you send me an email, I can think more about it and get back to you. But I know for a fact that I did think about this hard for at least a month or so at some point, probably about 2 years ago, and there were some obstructions. But it would be very nice if you could use some sort of identity, some method of rotations type thing to reduce the weak L1 inequality to the one-dimensional directional Hilbert transforms. That would be very nice. But there are some obstructions.
Okay, thank you very much.
Okay, thank you. I have a question, but myself, but probably is that I know in the linear case a result for proving multilinear linear estimates, that is Rubio de Francia extrapolation. If you know this, this result also is available in the case of multilinear Calderón-Zygmund operators.
Yeah, I'm trying to think of a paper that I might know. So I'm going to say with about 99% confidence that I'm sure that it is true. You would have to look into papers that sort of the king, the person I know who does this is Cruz Uribe. He's sort of, in my mind, the king of extrapolation currently. I can't recall off the top of my head if he has a version of extrapolation for the multilinear setting. There's a paper of Cabe Moen and I believe Sun, where they prove what the A2 conjecture for the multilinear setting. So they prove the optimal dependence for the strong type inequalities. And I'm pretty sure that their proof relies on multilinear extrapolation. So this has the multilinear sharp bound, the multilinear version of the A2 theorem. I'm pretty positive that their proof to go from the one exponent to all of the exponents will rely on a multilinear extrapolation. They would definitely at least mention something in that paper. I just can't remember where that would be proved by itself. But I'm gonna say with 99% confidence that it holds.
Thank you very much for this. So, okay, maybe you can stop sharing. It's a tradition in our seminar that some of the organizers makes you one informal question. So, Boris, have you one informal question for Cody?
Yes. Again, thank you for your interesting talk. Yeah, it was informative. Yeah. So first question is, do you think the mathematics is art or science for you? What do you think? It's for you, like, not general.
For me, mathematics is a game. So I don't know if that's art or science. I just think it's a fun game. It's a puzzle where you have some rules and you have some pieces and you want to move your pieces around according to the rules. You can see what type of things hold true. So it's kind of like a game of chess. I like chess. So I don't know, maybe to you, is chess a science or is chess an art?
Okay, so you cannot, maybe it will be third option, that is it game for you? Maybe, yeah, it's interesting. Yeah, it's new answer for me. Second is, do you invent or discover when you play these games?
I think both. So it depends on what you're doing. You can invent definitions and you can, but once you can invent axioms, but once your axioms and your definitions are invented and set in stone, I think that's something that humans kind of create. But once they're invented and then you prove theorems based on these axioms and definitions, then it's discovered. So it's really, that one to me is not so binary. It's going to be both. Different aspects are invented, different aspects are discovered.
Okay. And next question is that, so you're doing harmonic analysis, and I think their game is different than what PDE's games, right? Like it's, and the scale, like if you're doing PDE is kind of in our world, but for me, like harmonic analysis is more like in atomic level. And how do you kind of zoom in and zoom out when you game, like, or lose yourself like in some small location and zoom out? and keep off track, like where are you? Because if you go zoom in, like, you know, it's difficult to see what you're doing or lost yourself.
Okay, that's the question I've never been asked before. So to keep track of there's different things, different levels in zooming in and zooming out. So, well, I think there are different points in the research process where it's necessary to be zoomed in, and different points where it's necessary to be zoomed out. So when you're trying to figure out what an interesting research question would be, I think it's good to be zoomed out and think at a high level. To think about what is an interesting question, why is it an interesting question, think about general strategies for proving something. But then once you have an idea of here's what I'm trying to prove, here's why I'm trying to prove it, here's how I can justify why it's interesting, then you need to zoom in and work out all the details to actually rigorously prove something. So at different steps, you're kind of brainstorming questions, maybe seeing if something is interesting or not, deciding, trying to come up with just general strategies. But then when you're actually executing things, it's important to zoom in. So I guess it's important to be cognizant of where you're at in the research process, and being able to shift between zooming in and zooming out kind of consciously and intentionally.
Yeah.
Doing it in different fields, I'm sure this is something that exists in different fields. If you're working in PDE, maybe you're more often zoomed in or zoomed out. If you're doing this in harmonic analysis, maybe you're more often zoomed in or zoomed out, depending on what types of questions you want to think about. But I think that's a feature of any area of math.
Yeah, I think sometimes some people, when they they use harmonic analysis on PDE, they get some problem, zoom in and get some solving problem, and zoom out and solve this problem in PDE. Yeah, maybe. Okay.
Yes, and especially if you're working at the interface, like the intersection of multiple fields, especially harmonic analysis and PDE.
Yeah,
if you want to use PDE techniques to solve a question in harmonic analysis, or if you want to use harmonic analysis to solve a question in PDE, then the process might be slightly different.
Okay.
Thank you.
Thank you. Thank you very much, Cody, for your talk, and thank you to all the participants for connecting. Next seminar, we will have Federico Castillo from Universidad Católica de Chile, I think. So you are welcome to connect. So thank you. See you next week.
Thank you all. This was fun. Thank you.